Hello everyone, today we are going to talk about section 4.8, row space, column space and null spaces, which are generally called matrix spaces. So let's start with definition. Imagine that we have matrix with size m by n, not square matrix. I'm going to write down first few coefficients, so a11, lots of other numbers, a1n, lots of other numbers, am1, and some other numbers, amn. So we're going to deal with non-square matrices, and I'm just writing down corner elements. So guys, by definition, we are going to call space or span of row vectors. Row vectors are vectors which you get by cutting this matrix into rows. So let's kind of write it down. So imagine that row number 1 is going to be a11 and a1n. Row number 2 is going to be what? a21, a2n. We do see that these are vectors and all them belong to Rn, right? We can make a span of these vectors. So span of these vectors row 1, row m, and this span is going to be called row space of matrix A. So it's not just the general row space of n dimensions. No, it's going to be a row space of specific matrix A. So different matrix A is going to produce a different row space. So if you kind of make a span of these vectors. And same way we are going to define column space. Definition. Column 1 is going to be what? If we cut our matrix into columns instead of rows. So column 1, a11, and eventually am1, right? Column 2 is going to be a12 and am2, and so on until we reach what? Cn. We are going to have how many coordinates here? M. So all these vectors are going to belong to Rm. Now, span of this C1, Cn is going to make column space of matrix A. Of A. Okay. And maybe I'm going to show you example of row space and column space, and then we are going to move to null space. Okay, let's consider matrix A. Example, matrix A, my standard matrix. 1, 2, 3, 4, 5, 6. So what are going to be my row vectors? Row vectors are going to be row 1, 1, 2, 3, and row 2, 4, 5, 6. What is going to be row space? Row space is going to be all vectors W, which are going to be linear combinations of some constant. Oh, maybe I should use a different letter for a constant. Yeah, guys, sorry. Because I'm going to place C for column vectors. Constant 1, row 1, plus constant 2, row 2, and all possible combinations with all different keys, which are going to be just like real numbers, is going to produce some vectors W, and these vectors W are going to make our row space. Now, columns. Column 1 is going to be what? 1, 4. Column 2 is going to be 2, 5. And column 3 is going to be 3, 6. Well, column space is going to be all vectors, I don't know, U for example, which are going to be K1, C1 plus K2, C2 plus K3, C3. So all possible linear combinations with all possible different coefficients k are going to make span, and this span is going to be column space of matrix A, right? Okay, so what is next? The last space we need to talk by definition is going to be null space. Definition. Null space of matrix A is going to be a solution space of linear equation AX equals 0, so of homogeneous linear equation, so solution space. We already have seen this, that solution space of homogeneous equation is making a space itself, like because we have all possible linear combinations, like of some vectors with constants or parameters p, t, whatever, and they are making a vector space. Okay, so well, these are like major matrix spaces: row space, column space, and the null space. Now guys, what is interesting? The theorem. If we write down non-homogeneous equation AX equals B in the form of like linear system, something like this, A11 x1 plus A1n xn equals B1 and some other coefficients, AM1 x1 plus AMN xn equals BN, sorry, and some more equations in here. What we can see that these coefficients are making column 1 of matrix A. The next coefficients are going to make column 2 of the same matrix, and these ones are making column n, right? And if you write down this system like in the form of like product of x1 by column 1 plus x2 by column 2, sorry, column 2, and eventually eventually xn by column n, it's supposed to be equal like a column vector b, right? That's a similar vector to these vectors. What we see, guys, if we look from the point of view of linear combination, what we have actually, we have a linear combination of vectors C1, C2, and Cn with coefficients. This is coefficients, and these are vectors. And it looks like vector B is a linear combination of column vectors. So the theorem is going to tell us that the system AX equals B is consistent, has solutions. And what are going to be solutions? Actually, this axis, right? Axes are solutions, and in the same case, they are coefficients of linear combination. Is consistent if and only if both directions B, vector B, belongs to column space of vector A. So vector B is actually linear combination of vectors of column space of matrix. Well, that's basically the theorem and the proof of the theorem at the same time, right? I'm going to label this as a theorem 1. Well, guys, for theorem 2, I don't know if I'm going to prove it. I think we are going to leave the proof for class time. But I'm going to represent solution of consistent means which has solution, consistent non-homogeneous system, can be expressed as x equals x0 plus c1 x1 plus some ck xk. And you probably remember I was calling this particular solution of non-homogeneous system. just one possible solution of non-homogeneous system. I was calling this part as general solution of homogeneous system. You probably remember. And any general solution of this system can be represented as a sum of any particular solution of non-homogeneous system, just one singular solution, plus general solution of homogeneous system. I'm going to write it down, AX equals 0. Why does it work like this? Well, just imagine that you kind of check what is going to be x, this one, minus x0. It's going to be c1, x1, ck, xk, solution of homogeneous system. Well, if I apply a over this and I apply a over this, I'm going to get 0. Just because this is homogeneous solution and it's supposed to be equal to 0. So difference between any possible solution of non-homogeneous system and particular solution is supposed to be a homogeneous solution. And if you write down a x equals b and a x0 equals b, this is kind of some solution of non-homogeneous system. And this is particular which we used for the solution. If you subtract them, you are going to get a x minus x0 equals b minus b, which is going to be equal to 0. So you see that this is must. The solution of non-homogeneous system is a particular solution plus general solution of homogeneous system. Okay, we're going to see it on examples. Now, if we want to know the basis for this, vector spaces, how they are going to look. Well, guys, let's talk about what we usually perform on matrices. Usually, we perform matrices row operations, right? Elementary row operations. Well, what row operations are doing? Multiplying rows by numbers. Else, what they are doing? They are adding another row multiplied by a number or subtracting. Basically, guys, they are adding or subtracting or producing something what we are going to call linear operations on them. So, for example, you take row number 1 minus 2 row number 2. Well, basically, you take vector 1 minus 2 vectors 2. And it's not going to change the space of this row vectors. Just you take one vector multiplied by 2, subtract from another. I'm going to write down the theorems, the set of theorems, which is kind of what is going to be saved when you do row operations. But for the proof of these theorems, I think we can do them in class. It's going to be a very long lecture if I do all the proofs. So theorem number 3, elementary row operations don't change the null space of a matrix. Well, why does it happen? For this theorem, it's easy to understand. Remember that how do we solve actually linear system? Well, by doing these elementary operations, right? And if they were changing the solution, we would not use them to find the solution, right? So the idea is that if the system has a solution, by doing row operations, you are not going to change it. You are not going to get a different solution. So, okay. What also does not change? Next theorem. Theorem number 4. Elementary row operations don't change row space of the matrix. Matrix A, which we Well, again, Why they don't change row space? Because row space consists out of all possible linear combinations. And if you apply row operations, they're just going to kind of make these linear combinations slightly more like complicated or whatever. I'm going to show you like one example. I don't want to prove it as a general theorem. I'm just going to show an example. Imagine that we do have this vector W, that's row space, which consists out of constant 1, row vector 1, plus lots of other row vectors, and eventually row M. Like we have m rows in the matrix, and that's all possible linear combinations. When you do row operations, what you can do? You can exchange row number 1 and row number 2, for example. Well, obviously that the resulting set is still going to kind of describe the same vectors, because for linear combination, it doesn't matter where you exchange row number 1 and row number 2. Second, we can multiply a row by number. Well, if you multiply row by number, let's multiply row number 1 by number, like by any number, by constant. It's still going to be a linear combination, right? It's just going to be a linear combination with a different constant. And the last operation, if you take, for example, row number 2 equals row number 2 minus some constant row number 1, like the third elementary operation, constant row number 1. What is going to happen to linear combination? Well, what we are going to have? We are going to have K1, row number 1, plus in K2, and instead of row number 2, we are going to have, like if you express this, this is old row number 2, this is new, right? We're going to have row number 2 new plus CR1 and all the rest of linear combinations. What we can do, we can open this parenthesis and combine this part together with this. Yeah, we are going to have a slightly different constant here. We are going to have a constant K1 plus CK2, row number 1. But over here is going to be the same row number 2. And sorry, I'm supposed to put old one here because I'm trying to kind of show that this one is going to be the same. So old, and this one's supposed to be minus. That's going to illustrate my point better. So instead of like row number 2, I'm using my new row number 2. Now, if I open parentheses, I'm going to have this one with minus, sorry, but still going to be a number, row number 1, and that's still going to be an old row number 2. So basically, nothing changes when you do all possible row operations. Well, which means that the whole space, or like all these possible vectors, are not going to change too. Next theorem. Theorem number 5, and again, I'm not going to prove it. Unfortunately, row operations are changing column space, because when you do row operations, you are modifying columns themselves. When you do row operations on rows, you basically you create a new rows, but when you plug them in back, they're still going to belong to same linear combination. But when you do row operations, you are changing columns because you are kind of modifying numbers which belong to like different columns at the same time. So for columns, unfortunately, same statement is not true. So elementary row operations are changing column space, but they do not change the fact that columns were linearly dependent or linearly independent. So I'm going to write it down. Row operations don't change the fact that the columns were linearly dependent or linearly independent. So if some columns were linearly independent, they are no matter which row operations you do on them, they are going to stay linearly independent. If some columns are row dependent, they are going to stay dependent. I'm going to prove this in class. This is going to prove a little bit longer than the theorem 4, okay? Well, so now last theorem here, which is going to help us to kind of find the basis for row spaces and column spaces. If a matrix is in row echelon form, then the row vectors with the leading one form basis of row space, and columns with leading one make basis for column space. Well, I'm going to explain this theorem in class too, okay? Now I'm going to just consider example of like a row echelon form of the matrix and kind of describe like what is what here. Example. Well, you probably can kind of see like why it's like working like this. Imagine somebody gave you a matrix and you do all these elementary operations on it, and you got row echelon form looking like this. So you see that row number 4 totally disappeared. What does it mean, guys? It means that by subtracting or adding other rows to this row number 4, we kind of subtracted all row number 4. Means that row number 4 consisted out of, for example, linear combination of row 1, 2, and 3. Well, I don't know if it's actually row 1, 2, and 3. Maybe it's just 1 and 2. But consisted out of linear combination of other rows, I would say, in general. That's why it disappeared. But if row does not disappear, means that it's not a linear combination of other rows, and which means that they are linearly independent. So what we have over here, we have 1 leading one, 2 leading ones, and 3 leading ones. And we are going to have 3 linearly independent rows. Row number 1, row number 2, and row number 3. So these rows are going to make our basis. For columns, we are going to have column number 1, right? Column number 2, linearly independent, and column number 4. Number 3 does not have leading one. Number 5 does not have leading one. So these 3 columns are going to be linearly independent. They're going to make a basis for row space and basis for column space. So for column space of A, and these two are basis for row space of A. Well, kind of not difficult. Just find that reduce matrix to row echelon form and look at leading ones, right? Now, sometimes we will need to find which vectors which we have over here, C1, C2, C4, or R1, R2, R3, are not the same vectors which were in original matrix A. Original matrix A probably has different set of, so this is already modified one. And the basis we get the basis of modified matrix, right? But sometimes we have a question of finding the basis from certain vectors, not like modified vectors. So these are going to make the basis for column space and row space, but they are not the same vectors as vectors of matrix A, right? But usually you probably remember that if somebody gives you several vectors, for example, you have three-dimensional space and somebody gives you four vectors, you can always find the three vectors which are making the basis for this three-dimensional space. Well, unless all four are linearly dependent. Well, so now we'll try to solve a different problem. How to find which vectors are linearly dependent and which are not linearly dependent. Because what we have with modified matrix, we are going to have modified vectors. But what if somebody wants to know which original vectors are linearly dependent or linearly independent? Well, there is an algorithm how to find it. So I'm going to consider my example number 2. Example number 2. Imagine somebody gives us three vectors. 1, 2, 3. Vector 2 is 0, 2, 5. And vector 3 is 1, 3, 3. You probably will tell me, well, why don't we put them in a matrix, find out which are going to have these leading ones, and these vectors are going to be linearly independent. Yes, guys. The only little difference here is that when you do row operations on matrix, you can switch rows. So, for example, you have leading 1 for row number 2, but this row number 2 may be original row number 4 because you are switching them. And it's making life very, very complicated to keep track of what happened, which actual row is this. We do have them that independent, but what is row number 2? Was it row number 3, row number 1, or no, row number 5? Maybe we kind of switch them. So we are going to, instead of using rows, which are not going to keep track of position of the vectors, we are going to use columns. Because when you use row operations, you do not switch columns. So you are not switching column number 1 and column number 2, for example, when you do row operations. You switch only rows, right? Why does it happen? Well, if you do switch columns, means that, for example, you have solution x1, x2, x3. When you switch columns, you instead of x1, x2, x3, you are going to have x3, x1, x2, for example, which is not going to work, right? So what I'm going to do, guys, I'm going to make up a matrix which is going to consist out of columns from these vectors. So I'm going to put them into columns. 1, 2, 3, 0, 2, 5, and 1, 3, 3. So I put these vectors into columns. Well, they are probably all linearly independent. Who knows? Or maybe two of them are linearly independent. Or maybe actually all three are proportional to each other. Well, we see it's obviously not the fact, right? But again, I put them into columns because of that theorem which we are going to prove in class, that independence or dependence does not change from row operations. So if we find independent columns, they are going to be the same independent columns from V1, V2, and V3. And I'm going to do row operations on this matrix. So I'm going to take, well, row number 1 is already having 1 over here, so we don't need to do anything with it. So I'm going to modify row number 2. Row number 2 equals row number 2 minus 2 row number 1, right? And I'm going to simultaneously modify row number 3 minus 3 row number 1. So my matrix is going to look like this. 0, 2, multiplied by 2, 2, 2, 1, and 3, 0, 5, nothing changes here. And if I multiply 1 by 3, subtract from 3, I'm going to get 0. Okay. And so I kind of modified my first column. I'm going to start working with my second one. Well, I'm going to turn into 1 over here and have 1, 0, 1, 0, 1, 1 half, 0, 5, 0. And basically I just need to eliminate this 5, and that's going to give me like all leading ones or maybe non-leading ones. How to eliminate 5? I'm going to take row number 3 minus 5 row number 2, right? So let's have 1, 0, 1, 1, 1, 1 half, 1, 0. If I multiply 1 by 5 and subtract from 5, I'm going to get 0. If I multiply 1 half by 5, it's 5 over 2 with minus 5 over 2. And, well, you can always modify it into 1 just by multiplying by negative 5 over 2. So I'm going to just kind of erase it and just kind of write down 1 instead. And write down operation was row number 3 multiplied by negative 2 over 5. So guys, how many leading ones do we have? Well, we have 1, 2, 3. How many columns are going to be independent? Column 1, column 2, and column 3. So all 3 are linearly independent, which means that all 3 vectors are linearly independent. So they are making bases in this space. Well, that's how we are going to actually find bases for the space. Now, what if you want to find the basis of, like, somebody gives you a matrix and somebody is asking you, well, you know, this matrix has row space. How to find the basis of row space? I'm going to write out example number 3. Basis for row space. Well, we know that when we do row operations, we can switch positions of like rows in the matrix, and then it's going to be hard to say like, okay, these rows are linearly independent, but which original rows belong to like correspond them, we don't know. So what we do, guys, to find the basis for row space? Well, I'm not going to do the operation, but I'm going to just show you kind of how it's going to work. Imagine that somebody gives you matrix A, and that's 1, 2, 3, 0, 5, I don't know, minus 1, 1, 0, 3. Again, just arbitrary matrix, just out of my hand. And we have rows 1, row 2, and row 3. 1, 2, and 3. And we kind of want to know like which ones of them are linearly independent, or maybe they are all linearly dependent, or whatever, like which ones are making bases. Row 1 and 2, or row 1 and 3, or all 3 of them. What we are going to do, guys, I'm not going to actually do the operations, but I'm going to show you the way how to do it, because it's kind of very long to calculate everything. We're going to convert these rows into columns, do A transpose. And we're going to write down 1, 2, 3, 0, 5, minus 1, 1, 0, 3. And for this matrix, if we do row operations, because we converted these rows into columns, we're not going to switch position of them. And if we find, for example, row number 1, or column 1, and like, I don't know, like if we find which columns are linearly dependent here, they are going to give us the rows which were linearly independent in the original matrix. Well, I don't want to actually do the whole operation, but imagine that we did this reduced row echelon form and we found that C1 and C3 will have leading ones. C2 does not have leading ones. Well, like, or, oh, it's not actually good. I'm going to, yeah. And then we are going to say, then row number 1 and row number 3 are making bases. Of row space of matrix A? Well, I don't really know because I did not do operations. I did not actually reduce this to row echelon form. And it looks to me right now that all three are going to actually be linearly independent. But like, imagine that 2, then you are going to have the very same, the numbers which correspond to columns 1 and 3. So row number 1 and row number 3 are going to make bases. Well, again, while looking at this matrix, it looks to me like that all are going to have leading ones. But like in case like not all, then you choose only the rows which correspond to columns with leading ones. Okay, I think that's all for today, and you probably want to practice a little bit with matrices. Maybe I'm going to consider one example of finding general solution. In the beginning, remember, I was talking about this stuff. Let me go back. And I did not do any examples of that. Remember, I was talking about this theorem number 1, which is going to like have a solution of non-homogeneous system as a sum, or theorem number 2, as a sum of solution of homogeneous system plus general solution of non-homogeneous. I want to consider one example of this. Let's kind of move over here, and I'm going to do example. Or maybe below. Let's do below. Just I want to like write down. So that's going to be example number 4. Let's make it a different color, green, for example. Example 4. That's going to be a short example. Imagine that my homogeneous equation looks like this. x1 plus x2 plus x3 equals, I don't know, 7. Is it non-homogeneous equation? Yeah, definitely. But very short one, very easy to kind of find a solution, right? How are we going to solve it? Well, basically, you just solve it like this. Because we have like one leading one, and there is no more equations, we are going to set up x2 as a parameter, x3 as a parameter, and x1 is going to be what? 7 minus t minus p. No problem, tell me, what kind of solution is this? Well, I'm going to write down them in correct order. x1 and then x2 equals t and x3 equals p. I'm going to just illustrate like the idea of the sum of the solutions. Now, I'm going to modify it into a vector x1, x2, x3. And I'm going to write it down equals. And watch how I'm going to do it. First, I'm going to do numbers without like any parameters. It's going to be 7, 0, 0. We have 7 here, nothing over here, right? And then it's going to be plus, and I'm going to do t parameter. I have minus 1 for the top, right? I have just 1 for the middle one, and I have 0 for the last one. And next parameter, p. And I have minus 1 for the first one, 0 for the second, and 1 for the third. So what we see, guys, over here, this is particular solution of non-homogeneous system. This is general solution of homogeneous system. Well, let's check. Is it particular solution? Particular solution means that if you plug instead of x1 7 and 0, 0, 7 plus 0 equals 7. Yeah, it's a solution. So that's why we call it particular solution. It's not all solutions, but it's one of the solutions. And actually, there are you understand that different combinations of x1, x2, x3 is still going to be solution, right? Well, the second part solves homogeneous equation, which has actually no 7. If you had 0 instead of 7, your solution would look like this, like 0 here, and that's going to look exactly the same way, right? And solution is going to be only this part. That's homogeneous solution. Okay, that was the last example. Now we are going to stop at this point. Sorry, a long lecture, 40 minutes.